Okay, so just ignore this top stuff. I'm trying to save paper here. Um, so from the last video, we were talking about the four quantum numbers. And just before I go to Pauli exclusion principle, I want to show you how these four quantum numbers can then explain the lines close together in a spectrum for an element. So imagine this is n equals 3 and this is n equals 2. We've talked about how when an electron drops down, it emits a photon of energy that's equal to the difference in these levels. But then how come you can get multiple lines close together? Well, it's because in this n equals 2, you might have n equals 2, n equals 3, L equals 2. And if L equals 2, then you have an ML equal to positive 2, and an ML equal to positive 1, and an ML equal to 0, and an ML equal to negative 1, and an ML equal to negative 2. So within the n equals 3, L equals 2 subshell, you'll have these splittings. And then, of course, down here at n equals 2, you also have like L equals 1. And when L equals 1, then you have an ML equal to positive 1, an ML equal to 0, and an ML equal to negative 1. So really, when an electron is dropping from n equals 3 to n equals 2, it could be in any of these subshells, falling to any of these subshells. Now, there's not a big, huge difference in the energy here, but there's enough to make lines that are really close together. Okay, so it explains like the splitting of a line from one solid line to a whole bunch of little ones that if we could do a lab, you would be seeing. Okay, all right. So back to the four quantum numbers, and what we know is the Pauli exclusion principle. Okay, so Pauli was the guy that figured out the fourth quantum number. He was the guy that figured out that no two electrons could have the same address. Okay, and that's what his exclusion principle says. No two electrons can have the same four quantum numbers within an atom. Can have the same four quantum numbers. Okay, and this is no two electrons in the same atom, obviously. Okay. Another way that you will see it written as is that no two electrons can be in the same quantum state. Okay, it just means they can't have the same four quantum numbers. Now, to go hand in hand with Pauli's exclusion principle is Hund, and a few of you had Hund's rule. And Hund's rule says that electrons prefer parallel spins. Electrons prefer parallel spins when they are filling subshells, okay? So parallel spins in separate orbitals or separate subshells. So let me explain what I mean by that. It means like, okay, so maybe the easiest way is let's do one of these. So let's do sodium. Sodium, the atomic number is 11. And so we're going to have 11 electrons. So the first electron will go into the n equals 1. And when n equals 1, L equals 0. And when L equals 0, ML has to equal 0. And MS can either be positive a half or negative a half, so I'll start with positive. So this would be the four quantum numbers for the first electron in sodium. The second electron would be n equals 1, L equals 0, ML equals 0, and MS equals, it has to be a negative 1/2, because otherwise it would have the same four quantum numbers as the first guy, and it's not allowed. Okay, so now we're about to put the third electron in sodium. Can it go into the n equals 1 shell? No, because if it does, it will end up with the same 4 quantum numbers as one of the first two. So it has to go to the next one. It has to go to the n equals 2. And when n equals 2, L can equal 0 or 1. So you always start with 0. And when L equals 0, ML equals 0. And MS can either be positive a half or negative 1/2. So we'll start with positive. The next electron in sodium will go to the same spot. It will just have the opposite spin. Okay, when electron number 5 comes along, it goes into the n equals 2, but now it can't go into L equals 0. Because when it tries to go into L equals 0, all the possibilities, all the permutations or combinations, or whichever one it is, if you were a math teacher, is true. So it has to, remember we said when n equals 2, L equals 0 or 1. So now it has to go to the L equals 1. And when L equals 1, ML can equal 1. ML can equal 0. ML can equal negative 1. Okay, so it can have all three of these. So, okay, so MS then will be, let's say, positive 1/2. So the next guy comes along, goes into the n equals 2, L equals 1. Now, this is where Hund's rule comes in. Hund says that rather than this guy go into the same subshell, like go to n equals 2, L equals 1, ML equals 1, MS equals negative 1/2, it would rather go to a totally different spot, totally different subshell, the ML equals 0, and parallel spins. Okay, that's what it means, that they would rather parallel spins in the subshells. And so then number 7 would be n equals 2, L equals 1, ML is negative 1/2, MS equals 1/2. So it's like they put one electron in each subshell first, and then they go back and pair up. People will often talk about it's kind of like if you're going to live in a residence for a night, like you're on a bus and this big residence or hotel takes you in, that people would, the first ones in, would all go into their own room. And you'd only double up after all the rooms were full. And so that's what the electrons are doing here. They all go into their own room with the same parallel spin, and then when the next one comes along, it has to double up with one of these, because it always wants to go to the lowest possible state, the most stable state, okay? And so it's not going to hop up to the n equals 3. There's still space in the 2, but now they need to double up. So L equals 1, ML equals 1, and now MS equals negative 1/2. And then 9, n equals 2, L equals 1, ML equals 0, MS equals negative 1/2. And unfortunately, I ran out of space on the bottom of my sheet. So number 10 would be, whoops, that's an n equals 2, L equals 1, ML equals negative 1, MS equals negative 1/2. And then number 11, n equals 2 is full. It has to go to n equals 3. And then it will start back at L equals 0, ML equals 0, MS equals 1/2. Okay, and so there is how the 4 quantum numbers can be used to figure out exactly where electrons go in an atom. Now, when you look at this, it's like, this is pretty cool, but it might be a little tough to write out if I said to you, okay, so this evening I would like you to do it for uranium. And uranium's atomic number is 92. Imagine how long this would take to try to write out 92 electrons like this. There has to be an easier way. There has to be a way that we can simplify this down so that we don't take pages and pages and pages just writing out one configuration. Okay, but before we go there, so Pauli's exclusion principle is saying the spins have to be opposite, and Hund's rule is saying that when you get to the subshell L equals 1, they're going to